Today we are going to do another question, which is derive, derive the expression for frequency, which is going to be represented by n according to the question, of a vibrating string that depends on that depends on local that depends on load applied load applied, which will be represented by T, um, length of string represented by L, and mass per unit length represented by M. So that's the question. And in this question, it's not the question is only you might feel the question is difficult because it's not using the usual symbols that you would hope for, since frequency is generally represented by F, but here it's represented by M. Mass per unit length is generally represented by mu, here it is represented by M. The load applied is generally written as tension, but here it is written load applied, which might make you think that this is mass and not make you think that this is weight. So this is talking about the tension, which is the weight. So let's solve this. In order to solve this, if you know all the terms, what they mean, it's pretty easy actually. So here we have, since frequency depends on these factors, you can say that the frequency depends on tension to some power, let's suppose it is A, and depends on the length of string to some power, let's suppose it is B, and the mass per unit length M, suppose to some power, let's say C. So to remove the proportionality sign, we have to add a to remove the proportionality sign, we have to add a proportionality constant. So let's add K, which will give us this, and let's call this equation number 1, where K is a proportionality constant. So where K is proportionality constant, which is dimensionless. To do this method, we have to have a dimensionless constant in order to make it easy for us. So now let's see the dimension of every term involved. To do that, let's do it individually. The dimension of n here, n is frequency, so it will be per time, so after that, the dimension of T, which is load applied meaning tension, and tension in this case is the force, so it is a kind of force, so that will give us mlt minus 2. So this is something that people might be confused with, since it is said load applied, you might think it is mass, but it is actually talking about the tension. So tension is a force, so that's why we have to keep the dimension of force. Here L is length, so it will just be L, and finally M, small m, is not mass, so you might get confused and just write mass, which would be wrong. So in this case, we will have, this is actually mass per unit length, so it will be ml minus 1, because mass per unit length is not mass, even though it looks like mass, because generally mass is represented by m. In this case, it is mass per unit length. So here K is dimensionless. So now let's, since the equation is correct physically, which means the dimension of RHS and LHS must be equal, so the dimension n must be equal to the dimension of K, T raised to the power of A, L to the raised to the power of B, and M raised to the power of C. Here the dimension of n is T inverse, whereas the dimension of K is it is dimensionless. The dimension of T is mlt minus 2 raised to the power of A. The dimension of L is L raised to the power of B. The dimension of M is ml minus 1 raised to the power of C. So now let's simplify this a little bit. So here there is only two m's here, m raised to power a and m raised to the power of c. So we get that the m is raised to the power of a plus c. After that, let's look at L. Here is L raised to the power of A, L raised to the power of B, L raised to the power of minus C. So we will get L raised to a power of A plus B minus C. And finally, T, there is only one T, so it is and it is being raised to a power of a, so we will get t to the raised to a power of minus 2a, since the original t was raised by minus 2a raised to a power of a. So now we can compare the LHS and RHS, equating power of the same base. In here you can also write this as m0 l0. So now we have to compare them. So equating equating power of same base power of same base on both sides to get the relevant equations. So let's go back and let's see. So checking out m, we get 0 must be equal to a plus c. So in order to write that, let's write a plus c must be equal to 0. Let's call this equation number 2. After that, 0 must be equal to a plus b minus c when looking out at L. So we have a plus b minus c to be 0, which is our equation number 3. And finally, looking at t, minus 1 must be equal to minus 2a. So minus 2a must be equal to minus 1, which will give us our equation number 4. So on solving from equation number 4, we can clearly see that a has to be 1/2. So a has to be 1/2. Then we can go to equation number 1. Since a is 1/2, then c will obviously be minus 1/2. Then let's go here. Here a will be 1/2 and c will be minus 1/2. So it will be 1/2 plus b minus 1 by 1/2 equals to 0. So 1/2 plus 1/2, that means it will be 1 plus b equals 0. So b will be minus 1. So this is pretty simple calculation, so I'm not going to show how to solve it. Just find the value of a from equation 4, find the value of c from equation 2, and find the value of b from equation 3. So now we have ABC, so let's write the equation. So we know frequency is k times t raised to a power of a, and in this case a is 1/2, and after that L is raised to a power of b, which is minus 1, and mass per unit length m is raised to a power of c, which is 1/2, which means n is actually k, k by l square root t by m. And this is actually a this equation is actually a relation that you have to learn. In a later video I will teach you that. So this is actually the answer, but let's write some extra points. So experimentally the value of k is found to be a 1/2. So this is the 1/2, and this is actually for the fundamental frequency, which we will learn later. This is a special case, basically, when we're just talking about a string that's vibrating in its fundamental when it's in its fundamental frequency. So hence, therefore, frequency of vibrating string, vibrating string n, so will be 1 by 2l square root t by m. Even though these are not the usual symbols, we must use the symbols that the question says us to use in order to have consistency. So this frequency is actually when, so let me draw a figure. Let's have two supports. So these are support beams. This is just extra information. This is not relevant to the question. I mean, it's relevant, but it's not that relevant to the question. And let's make a, so suppose there is a string here. So this is the string, um, so let me change the color of the string. So this is the string. So if the string vibrates, and the string has to vibrate in a specific way, so how the string must vibrate, let me draw that. Let me copy this, let me move this here. So for this frequency that we found, the string should vibrate like this. I have not drawn it, this is just my arrow representation. So let's draw this. Suppose I plug the string from the middle. So I went here and plugged the string. So let me draw. How does a hand look? Does that look like a hand? Um, so how many fingers does a human have? I mean, I know it, but um, I don't know how to pluck it, how to draw the plucking. So if I, let's just do the basic. So that's the finger, and if I have to pluck it, then I will obviously use a thumb. So there's my thumb, and that's my hand. So I'm plucking it. So when I plug it, suppose I pluck it upwards. Let me use another color. Suppose I pluck it upwards, then the string will actually vibrate like this. Um, so going up like that, and the string will vibrate up for some time, and it will also go down. So it will um, it will move going like this. So it's not that it's, so let's fix this quite a bit. um yeah, like, yep, this. So as you can see, in one moment of time, when I plug the string, it will move up, then it will go down. So it will, if it's moving very fast, it will look like this. So that's the frequency of finding. Since the string can be in various arrangements, for example, the string could actually vibrate like this, creating two specific things, or even three, like this. But this formula is just for that case, when it's the string is vibrating like this. If, this is actually the superposition case. So actually the string will be like this, then the string will go like this. It will move from this phase to that phase. So combining them actually leads with this. So that's it with today's video, and in the next video we are going to do some more questions. Till then, bye bye.